Good morning, everybody. So today we shall start the discussion on optical source laser. Laser, as you know, is basically the full form is light amplified stimulated energy radiation. So typically, efficiency of lasers is much more than the LED or thermal sources. More than LED. So this is because there is some kind of optical feedback which gives rise to this stimulated energy radiation. So there are gas lasers and semiconductor lasers. So in case of gas laser, usually it is called that some kind of population inversion, so which gives rise to the stimulated energy. And in case of semiconductor lasers, it is effective inversion. Effective inversion is nothing but increase of the carrier population to a very large value in a small active area or narrow active area. So that gives rise to the stimulated energy radiation plus this optical feedback. So in case of semiconductor lasers, population inversion is replaced by effective inversion. So for the gas laser, actually the population inversion takes place like this. You have a ground state. Then you have pumping energy. So the energy level is reached to say state 1. However, the lifetime lesser lifetime of the order of nanosecond or less than or less. Then there is an intermediate state where say state 2 of higher lifetime, nanosecond or more. So then the population of the ions, energetic ions at this state will be higher. because it has higher lifetime. So there will be unstimulated emission. There will be one emission here also. So because this gap is lower, so the energy delta Eg here, delta Eg1, delta Eg2, and of course the natural state is the ground state. So because here together at a time large number of carriers will be releasing its energy to a ground state, so therefore stimulated energy, stimulated emission takes place. This stimulation is further enhanced by optical feedback. So how this optical feedback so optical feedback is made by placing two pieces of mirrors this is fully reflecting mirror and this is partially reflecting mirror. So when a energized ion release its energy and emit a photon, so that photon will be reflected back and forth in this what is known as cavity, usually in a very low pressure. So the photons which are basically reflected back will have a time delay, so therefore they will have a phase difference. And with the next emission, if this phase difference is constructive, then at that point the intensity will grow. Otherwise, what will happen? The energy will be absorbed by the charged particles if the emissions are not in phase. So therefore, by putting two reflecting mirrors and the photons getting bounced back and forth, we are forcing the emissions to be phase matched. and therefore the there will be a filtering effect as well, and also there will be a directed nature of the laser will come, though there are some amount of optical collimation is done at this point. So this is typical gas laser, and this pumping can be done by pumping energy by optical method, that can be done by flash lamps, xenon lamps, etc., or electrical discharge. That is, there will be a high voltage spark will be created in a low pressure gas, so there will be emissions. So now, in case of semiconductor lasers, of course, this is replaced by effective inversion. So effective inversion in case of semiconductor laser is controlled by the gain and absorption in the medium. As you can see that in a cavity, the constructive interference need to have a positive gain, and that way the optical feedback will matter. Now, in case of semiconductor laser, also same thing. Only thing here, the gain is controlled by the energy of a photon. Gain is 0. When photon energy h omega less than the band gap energy. So typically, the gain is increased by increasing carrier injection. So that is by injection current. So if we compare the current drive, the LED and laser diode, for laser diode, current drive requirement is much more, an order higher than the LEDs. If we gain curve, this side is energy. So this corresponds to Eg of gallium arsenide, 1.424 electron volt. So typically, if we have a carrier concentrations at lower carrier concentrations like 1.5 into 10 to the power 18 per centimeter cube, we will have a gain curve like this. But if we increase this one, so if it is increased, so the gain curve will grow, and we have a positive. So the area under the curve above 0 is the positive gain side, and the more is this area, actually we will have more radiation, sustained radiation. So here the carrier concentration is 2.5, say 10 to the power 18 per centimeter cube. Now to achieve such high carrier concentration, the construction of the device has to be made from very pure material, and the process need to be controlled in an accurate manner. Otherwise, such kind of high carrier concentrations will give rise to random recombinations, and thereby heating effect will dominate, and the device will be heated up too much to operate in a stable fashion. So now, just like LED, we will have this laser also constructed in a similar fashion, heterostructure. However, typically the layers thickness is much less. For example, if we consider the structure of a gallium arsenide laser which emits in near infrared, P-type gallium arsenide, then gallium aluminium arsenide, Ga1 minus Y, ALY, AS. Then there is a narrow layer, which is the active layer. So construction wise very similar to the semiconductor LED. If we just compare in the previous gallium aluminum arsenide that we have discussed. Only thing, the layer thickness of this layer is much lower than typical LED. It could be say 0.2 micron in case of ternary semiconductors, 0.2 micron to 0.1 micron or so. It is much more thinner in case of say various modern lasers, high efficiency lasers, which are known as multiple quantum well laser. So where thickness goes down to nanometers, 10 nanometer, 20 nanometer or so. So this surface is known as the clipped surface. So this means this has been cut parallel to the lattice plane. Because the smoothness of a surface depends that how we are breaking it or cutting it. So if it is cut parallel to the lattice plane, so then all the lattice points or the atoms will be aligned or terminated almost at the same distance. So therefore this will be very shining surface if it is cut. So because it is a shining surface, so therefore this will act as a partially reflecting mirror. And this side is fully reflecting mirror by making some kind of dielectric coating. Then we can have electrode here. There is a refractive index difference of the NGAS and gallium aluminium arsenide or aluminium gallium arsenide, whatever we call it. So which guides the radiation. So it can be like this. The refractive index difference depends on this stoichiometric ratio x, and approximately it could be 0.62 s. And if we have Eg is also dependent on x. Eg as a function of x would be 1.424 plus 1.247x. This is the band gap energy of aluminium arsenide. This is the band gap energy of gallium arsenide. So delta Eg, which is responsible for the carrier confinement, would be approximately 1.247x. Now, unless construction is controlled, like deposition of these layers is controlled very homogeneously, the defects may give rise to heating loss. There are other effects as well, which is the radiation confinement. Tend to deteriorate beyond certain thickness. Of active layer. In case of quantum Weyl laser, it is, of course, interpretation is different. But normal lasers, the radiation leaks out if the thickness goes beyond λ/4. This is the central zone. So this is for 0.2 micrometer. However, in case of 0.1 micrometer, it could be the radiation tends to leaks out. And as well as the carriers. So due to the tunneling effect. So this is, for example, for a case of base refractive index of delta n would be 0.1 and base refractive index 3.6. The structure is further modified to improve the efficiency two-dimensional and three-dimensional confinement. Of carriers are designed. Now, usually there is one important aspect that for laser is the threshold current. Which is again depends on active layer thickness. So it almost increase linearly in micrometer. Threshold current in milliampere. So this is say for double heterostructure carrier confinement. And this could be simple structure. Now, this portion is basically the spontaneous emission. Below the threshold current, spontaneous emission dominates below threshold current. Threshold injected current density JT J small t, and this is J capital T. This J capital T is the transparency current. Transparency current corresponds to the amount of emission at which the medium will be transparent at that wavelength. So that means one more photon emits, so that will go out of that medium without any loss. So that's why that particular current is known as the transparency current. So this is related by charge of an electron, length of the cavity, that is the active layer of the device. This is quantum efficiency, recombination lifetime. Carrier concentration. E is charge of electron, L is the length, L is the thickness, L is the thickness. Now alpha is the resonator cavity loss coefficient, and alpha is the total loss. Loss factor or gain factor overall. Current I could be J into A could be, or like IT is equal to JT into A. A is the width and length, that is the cross-sectional area. So if we take one example, take the example of threshold current of indium gallium arsenide phosphide laser. So delta NT in one case it is 1.25 into 10 to the power 18 per centimeter cube. Say alpha is 600 per centimeter. Tower 2.5 nanosecond. Refractive index N 3.5. Eta I quantum efficiency could be 0.5 to 1. So if it is equally probably, then it could be 0.5. D is say 200 micrometer, W is 10 micrometer. Yes, there was some power cut, so it could not be.